So Dave did his undergrad studies in engineering physics in the University of British Columbia in Canada, then master's and PhD at Cornell. He continued on postdocs at Caltech, McGill, Maryland and Southampton. And now he's lecturer, which is the assistant professor equivalent that we have here at the Department of Physics at the University of Bath. Dave has been working on various things. It's very hard to describe what exactly the many things that he is doing. I think that the best way to put it is that he's doing dynamics and astrophysics. So today he's going to tell us about resonant shattering flares as multimessenger probes of neutron star physics, which are very interesting and hot topic. So Dave, the floor is on you.
Oh, thank you, Kostas. Right, so thank you very much for the invitation to speak. So I'll be talking about some work that I've been doing for a while, but has, because of recent events, become very, very timely. So this is work I call Resonant Shattering Flares, and how they can act as multi-messenger probes of physics within neutron stars. Right, so we'll start, I guess, the right place to start is talking about what a neutron star is. So you may be aware that a neutron star is one of the end stages of stellar evolution. So if you have a relatively small star, it will, go through a red giant phase, eject a bunch of winds, forming planetary nebula, and eventually form a white dwarf. Whereas for a larger star, it will go through a red supergiant phase, supernova, and then has a chance of either forming a neutron star or a black hole, depending on its initial masses and metallicities. A neutron star is the most extreme matter in the universe. So you have something that's about the size scale of a small city, that has more than the mass of the sun, spinning at, with periods of, as low as tens of milliseconds, with extreme magnetic fields, which I'm sure Kostas can tell you a lot more about. Oops, what happened there? The interiors of neutron stars are equally as extreme. They're the only stars with a solid crust, for one thing. The matter is so compressed that all the electrons sort of run into the protons and they form neutrons, and those the ions get heavier and heavier and heavier in the crust. It forms a lattice in the crust, making it a solid, and then in the inner crust, you transition through the inner crust into the core, where you again have a fluid, but now it's a superconducting superfluid. And then within the neutron star, at the very inner core, we don't really know what's going on there. It could be hyperons, it could be quark matter, or it could be just more neutron fluid. Here's a quote from Sir Martin Rees, the Astronomer Royal in the UK. He says that the cosmos provides the only laboratory where sufficiently extreme conditions are ever achieved to test new ideas in particle physics. By studying things like neutron stars, we are learning something about fundamental physics. And this is very much the reason that people like Kostas and George and I like neutron stars, is because this is where we can really see the most extreme situations in the universe. In particular, if you look at a plot of the density in a given experiment versus the temperature that's probed by that experiment, you see that experiments like the LHC or the or RHIC, these different colliders, they sort of probe, not that dense and pretty hot, similar to the conditions in the early universe, right? Heavy ion colliders can sort of probe things with a higher density, but still are pretty hot. Neutron stars, however, get you into this part of parameter space where you have extremely high densities, but also relatively low temperatures per particle, low temperatures. So the neutron stars really inhabit this really powerful, they're really powerful laboratories to probe this part of parameter space that we cannot get to using terrestrial experiments. So here's some neutron star facts for you. They range, typically from 1 to 2 solar masses, so that's about 1 million Earths, but are only about 10 kilometers in radius. Their densities range from 10 to the 9 to 10 to the 17 kilograms per meter cubed, and they can have the largest magnetic fields in the universe. From sort of, a weak neutron star has a magnetic field of 10 to the 8 Gauss, which is already relatively unimaginable. But people like Costas like to study 10 to the 15 Gauss field neutron stars, and this is dipole field, which are the magnetars. Their temperatures are sort of high by our standards, but their entropies are low. In other words, we're nowhere near the Fermi temperature that it would take to sort of lift the degeneracy of the neutrons. The cores are known to be superfluid and superconducting. So if you're a condensed matter physicist, this is the real high temperature superconductor, not like these, fancy, room temperature superconductors that people are doing now with these high pressures. The fastest known pulsar, I think still current, is 716 rotations per second. And the gravity on the surface of a neutron star is about 10 to the 11 times larger than the gravity on the surface of the Earth. Okay, so if you took every single person on the planet and piled them into one giant cube, just like piled them one on top of another, it would, you could build a cube of people about this size. So this is a picture of New York City, of Manhattan. And you see the Empire State Building there, here for scale. And this is the tallest building in the world, the Burj Khalifa. So every single person on Earth, if you just pack them all in, could fit inside a cube this big. But if you put them on a neutron star, the gravity would compress them until they all fit into the size of a teaspoon. So that's how extreme the gravity is on a neutron star. Because that gravity is so strong, because there's so much matter there in such a small space, the curvature of space-time is strong. And these objects are dynamic. When you have two of these extremely dense, extremely small objects moving around one another, you get ripples of space-time, gravitational waves. In 2015, LIGO detected the first gravitational wave signal. This was a chirp of two black holes, two relatively large black holes, so large that you can kind of see the data by eye. And this sort of really opened up a new window into the universe for us, probing space-time itself and using that to see sort of the motions of the most dense, the most extreme mass in the universe. For those who don't know, LIGO is a giant interferometer that measures very small wiggles in the distances between the two arms. And so what happens as two neutron stars inspiral, they'll emit gravitational waves, and those gravitational waves will carry away energy and angular momentum, and that will shrink the orbit, and that orbit gets faster and faster and faster. And so you get a waveform that's called a chirp. So this waveform starts off small, and then it gets faster and faster and faster as you get closer and closer to the merger. And then right before the merger, it zips up really, really high frequency and really, really loud. Well, relatively loud. So a few seconds before the merger, you have a period of you have a frequency of maybe 100 hertz or so, and then right before the merger, you get jump up to frequencies of a few kilohertz. Okay, so one of the biggest discoveries of really the last century, I think, was GW 170817, which was the merger of two neutron stars detected by LIGO. Just from the gravitational wave signal alone, we could already put constraints on details of the neutron star physics. So here, this is a plot of the masses of the neutron stars. You notice that the uncertainties sort of make this swath. That's because what's best measured from a gravitational wave signal is the chirp mass, which is a combination of M1 and M2. Okay. There was no signature. I think I'll say that here. Yeah. Well, there was no tidal interactions there's no signature of the tidal interactions that were seen in the gravitational wave signal. So from that, you can already tell that it's sort of on the more compact side of these possible equations of state. Though we kind of already knew these, the ones that were out here that predicted 15-kilometer neutron stars were ruled out. So the reason that 170817 was so impressive was because they also happened to catch an electromagnetic signal from the same merger. A few seconds after the merger happened in the gravitational waves, the Fermi satellite detected a weak gamma ray burst. And this turns out to be what's called a off-axis short gamma ray burst. This is in the energies of a few 100 keV. This allowed them, the combination of LIGO and Fermi and a whole host of satellites searching the sky allowed them to track down the location and also see the what's called the kilonova that occurred immediately after the gravitational wave merger, the merger of two neutron stars. So the first signal was the short gamma ray burst. It was probably off axis. So a short gamma ray burst occurs when you have the material left over from the merger forms into a disk and then accretes onto the central black hole that is formed. That will launch a jet which shoots out at the observer. And you have multiple colliding shells that cause an internal shock wave that sort of get energy all the way up to the gamma rays. And that jet eventually collides with an external shock. So we see the prompt emission in these gamma rays, and then afterwards we see an afterglow, which occurs because the jet collides with the surrounding medium and transfers and loses energy. And then you get some X-rays, some visible light, some radio, sort of all in a sort of well-known cascade. Oops, what happened there? Okay. We also get a kilonova. I don't know what happened to that. Oh well. We also get what's called a kilonova, which is when the material from the neutron star is, hold on, let's see. Yes, I think that's just the wrong. Yeah, that's just the wrong order. So a kilonova happens because some of the material is sprayed out, and that material rapidly decompresses. And remember, a neutron star is so dense that all the electrons have been squeezed into the protons, essentially. And so all the neutron or all the nucleons are relatively neutron rich, or the neutrons are just sort of free streaming around. When you suddenly decompress them, the neutrons don't want to be free. They want to jump into nuclei. And so what happens as you rapidly decompress these nucleons, they all want to run together and hide inside these inside the nuclei, and those become very rapidly very, very heavy. But those very heavy nuclei are unstable. They have to beta decay into the neutrons like to beta decay into protons until they hit one of the nuclear physics magic numbers. So here's a simulation of what happens. So as you get this rapid decompression, you suddenly get lots of neutrons filling in these nuclei. And then they beta decay to get closer to these islands of stability, which are these black boxes here. Okay, so this nuclear decay, this provides the heat that heats up this expanding shell of material, and that produces what's called a kilonova. And this was observed by many, many optical and infrared telescopes following up 1708-17. And this also tells us that merging neutron stars are the source of the elements that are produced by this kind of process called the R process, the rapid neutron capture process. So here you can see the things labeled in orange are primarily produced by merging neutron stars. So for instance, most of the gold, most of the platinum, most of the valuable, the bling elements are actually produced by neutron star mergers. A friend of mine tried very hard to get everybody to call these bling nova rather than kilonova, but nobody listened to her. So, right. So, those are what was observed during 1708-17. There's lots more details about those that one could ask, but the kilonova and the short gamma ray burst really tell us about what's happening in the messy post-merger physics. Basically, what happens after the merger, right? There's a formation of a black hole, and then an accretion of a disk onto that black hole to make a jet. You also get, this material being sprayed out sort of asymmetrically, and then you get the radioactive decay of that material. But it doesn't tell us a heck of a lot about the neutron stars themselves, which is what I am primarily interested in. Okay, so for the rest of this talk, I'm going to focus on a different electromagnetic counterpart that provides a probe of neutron star physics, and this is resonant shattering flares, which I work on. And the reason that resonant shattering flares happen is because of the structure of a neutron star. So remember, we talked about how they had an atmosphere, a crust, an outer core, and an inner core. And this crust, the fact that this crust exists, is really what makes these resonant shattering flares possible. Okay. So one observational piece of trivia that I became aware of was that some short gamma ray bursts, which are, remember, short gamma ray bursts are thought to be the result of merging neutron stars. Some of these SGRBs have little blips that occur a few seconds before the mergers. So here's an example from Swift Bat, where there's actually two. I don't believe this one, but this one has a little blip, 0.5 of a second before the merger, as well as in both Swift Bat and Fermi GBM. Here, Suzaku and Swift both saw a blip a couple seconds before the merger, and similarly here for Swift and Fermi. So some of these SGRBs have precursors. But if you sort of take the model of these guys coming from mergers seriously, there shouldn't be anything going on a few seconds before they merge. So what is happening 1 to 10 seconds before the merger? Okay. Well, the key to thinking about this is realizing that, they interact a lot more than just right at merger, right before they collide. They induce tides on one another, right? So because when the neutron stars get close, one side attracts more than the other side, you get strong tides, for instance, like the lunar tides that the moon causes on the Earth. Okay. So an isolated non-spinning neutron star stays nice and spherical. A spinning neutron star gets deformed, but a non-spinning neutron star in a binary also gets deformed in a similar way. Now, this does imprint itself on the gravitational waveform, and there was some hope that we'd be able to detect them. And I think we indeed can after many, many detections. But it's a very subtle effect, and you need a very high signal to noise ratio in order to be able to see this, the signature of tides, what's called the love number on the in the gravitational waveform. Okay. But these tides will stretch the crust. They'll squish down and stretch out the crust. And you might ask yourself, well, if we can get flares from magnetars, when magnetars sort of pull on, where the magnetic field evolution pulls on the crust of the neutron star and causes it to fracture and launch out a giant magnetar flare that Costas knows a lot about. Maybe just the tidal squeezing can cause the crust to fracture. But it turns out that neutron star crusts are ridiculously strong. You need a shear strain, a delta R over R, effectively, for a change in, like a 10% change in the deformed radius in order for direct tidal crust cracking to occur. And that just does not happen until basically an effective frequency of a few kilohertz. So you'd be right before the merger, or probably after the merger. So direct tidal crust cracking, where you just have squished the neutron star down enough so that you get a fracture, it doesn't work. It doesn't occur a few seconds before the merger. So you can ask yourself, what else can happen? What else could cause something to give us an emission a few seconds before the merger? Well, if you have a perturbation that's weak compared to what you need, but it happens to occur at the right frequency, then you can cause something interesting to happen. The phenomenon of resonance, where you're perturbing the material at the correct frequency, at the natural frequencies of the object. And that can cause it to get to very large amplitudes, such that nonlinear effects like the shattering of this glass can occur. Okay. So let's take a look at tidal resonance. So neutron stars, they have normal modes, just like any other object. Any other object that's in equilibrium can have normal modes. Tidal resonance can transfer huge amounts of energy to those particular modes. So to get the energy out, you need a mode that strains the crust, because you need to sort of build up the energy in one place and then suddenly release it, which the solid crust is good at. You need to be able to couple to the tidal field, because if you can't couple to the tidal field, you can't get that, you can't deposit that energy to begin with through resonance. So you need an L equal to 2 spheroidal mode. So that's L as in YLM L. It also has to hit the resonance well before the merger. The fundamental mode of a neutron star, as we'll see in a little bit, is strains the crust and couples really, really well, but you don't excite the fundamental mode until you hit about several kilohertz, and by that point you probably have already smacked the two neutron stars together. Okay. So we need a mode that strains the crust, couples the tidal field, and hits the resonance. So the first thing you might think of is, what about what are called G modes, where gravity is the restoring force. If you look at the G modes of the core, you'll find that, the L equal to 2 ones are spheroidal, and they couple very well to the tidal field. They hit resonance at a few tens to hundreds of hertz, so that's actually pretty good. It sort of jives well with the fact that we see a precursor before the merger. But they don't really interact with the crust at all. So you have these modes rattling around inside the core, but there's no way for that energy to sort of build up and get out. Okay? So probably what happens with these is they do get excited, but they probably just rattle around inside the neutron star, heating it up a little bit. And then when they merge, any signal that you get from them would be swamped out by all the chaos that's happening during the merger. Okay, so there we saw that, okay, we want something that really penetrates into the crust. And one of them, you might think immediately, well, I can look at toroidal shear modes, which are by definition in the crust because the core can't support a shear. It doesn't have a shear modulus, whereas the crust does. So a shear mode provides a restoring force within the crust, so it definitely strains the crust. It again has pretty decent frequencies in terms of the timings, and you can get frequencies of tens to hundreds of hertz, but the L equal to 2 shear modes aren't spheroidal. Okay, they're toroidal, and so they do not couple to the tidal field. If you look at the overlap between the tidal field and that, it's basically 0. Okay. So these don't get excited, in other words, they don't get excited directly, I should say, by the tidal interaction. So they can't grow that large. The one that does grow the largest is the F mode. It strains the crust. It couples to the tidal field. This actually couples best to the tidal field. So if you can excite it, the F mode absorbs the most from the tidal interaction, but its frequencies are way too high. And you probably either will get it right before the merger or it'll have happened after the merger actually occurred. So we probably don't actually hit that resonance. We certainly don't hit it a few seconds before the merger. Okay. So it turns out that there is one mode, and only one mode, that satisfies our requirements. And this is the L equal to 2 crust-core interface mode. This is a mode that exists because there's a transition, because there's a sharp transition between a fluid core and a solid crust. The solid crust can support or has a shear modulus, so it can sort of have a restoring force against shear, whereas the fluid core can't. And so you get a peak at the core crust interface, at the core crust boundary of the of this mode. So the mode kind of looks like an egg. So if you imagine the core sort of forming an egg and then the crust sort of shearing out of the way and then pushing it back. So that's what the L equal to 2 core crust interface mode looks like. It definitely strains the crust. It couples to the tidal field and it hits resonance well before the merger. Again, at frequencies of tens to hundreds of hertz, depending on the equation of state. Okay. So I think what happens here is that the orbit transfers a bunch of energy through this tidal interaction into this resonance. That excites a mode, and that mode builds up until the crust hits a breaking strain at some point. Basically, you get enough energy that the crust sort of exceeds the breaking strain. And then you get a fracture, and then a bunch of that energy gets converted into seismic waves. This happens over and over and over again because this resonance is so strong. It keeps driving this. The crust heals pretty quickly, and this keeps driving it over a resonance window, which is about 1/10 of a second. You keep driving this, and you build up seismic waves so much that eventually you build up past the elastic limit where almost the entire crust hits the breaking strain. And then that shatters the crust and scatters the seismic waves to high frequencies. These high frequencies can couple to the magnetic field. The low frequency seismic waves from here actually don't couple very well to the magnetic field. You can sort of do the calculation. It's like impedance matching in coax cables, right? If you don't have the right impedance matched, almost all the energy gets reflected and nothing goes out. Whereas the higher frequency seismic waves actually couple very well to the magnetic field. So then the energy can be extracted. the maximum energy that can be extracted turns out to be a function of the magnetic field, the surface magnetic field squared. No, this isn't the dipole field. This is the surface field, which can possibly be significantly stronger than the dipole field, depending on the sort of multipole moments and details of the magnetic field of a neutron star. Okay, so these magnetic fields basically get shaken so hard, so nonlinearly, that they spark a pair of photon fireball. Basically, you accelerate electrons and positrons. Those emit gamma rays, which collide with the magnetic field and produce even more pairs, and then that blows out in a series of pair photon fireballs, which will collide with one another and then give us our emission of a resonant shattering flare. Okay, so 1 to 10 seconds before the merger, I think what happens is that tidal resonance excites a core crust interface mode. It causes a fracturing and shattering of the neutron star crust. The energy is then deposited into the magnetosphere, and it blows out in a isotropic pair fireball. Multiple fractures and shatterings occur, and you keep dumping these the energy out in these fireballs, which then collide and give you a non-thermal spectra. The upper limit to the luminosity that you can expect from this is about 10 to the 49 ergs for a 10 to the 14 Gauss surface field. This could go up or down depending on the magnetic field strength at the surface. So we might expect that the energy that you could see from these things is somewhere between 10 to the 47 and 10 to the 49 ergs, with a resonance width, with a duration, which is about the resonance width, which is about 0.1 seconds. Okay. There may be, so before I talked about precursors to short gamma ray bursts, but short gamma ray bursts are very, very beamed. They're pointed in a particular direction. They only span a few degrees. If that beam is pointed not towards the Earth, you may actually still see the resonant shattering flares that occur, because those are relatively isotropic. So you can look through the literature and look for things that have the right energies and right durations for them to be potential orphan resonant shattering flares. Basically, resonant shattering flares where you don't see the original short gamma ray burst. So you can ask the question, is there a local RSF component within the short gamma ray burst population? And there's some hints that there is room for such a population. Additionally, when you consider neutron star black hole mergers, for a large parameter space, you do not get tidal disruption. So this is the spin of the black hole versus the mass of the black hole. And this is for a 1.4 solar mass neutron star. And you see that if the mass of the black hole is bigger than about 5 solar masses, tidal disruption requires you to have a very high spinning black hole. And short gamma ray bursts and kilonova require you to get to that tidal disruption level. Otherwise, the neutron star will just get swallowed by the black hole, and you don't get sort of the classic electromagnetic counterparts. On the other hand, a resonant shattering flare doesn't require you to tidally disrupt the neutron star. As long as you hit that tidal resonant frequency in the orbit, you actually can cause a resonant shattering flare to happen. So the resonant shattering flares can occur for a much wider range of parameters, of black hole parameters in a black hole neutron star merger. So for this whole space, of this whole region of parameter space, resonant shattering flares may be the only thing that's happening the only electromagnetic counterpart that you can get from these neutron star mergers. Sorry, these neutron star black hole mergers. If the resonant shattering flare frequency is too high compared to the orbital frequency at the innermost stable circular orbit, then you just get the black hole swallowing the neutron star hole before it gets to that frequency, and you get no electromagnetic counterparts. So here's the same plot, but for a different basic equation of state, and you can see that you get a much wider range for this particular equation of state. So if you have different progenitors, you have a neutron star that can form either a hypermassive neutron star with a disk and ejecta, a black hole with a disk and ejecta. A neutron star black hole can also form a black hole with a disk and ejecta, or just a black hole if there's no tidal disruption. And a black hole will just form a black hole. And assuming that there's no matter around, you don't get any emission. So the classic emissions from these are the killa/macronova and SGRB, whether it's off axis or not, which includes the prompt and the afterglow. In both these cases, you require some sort of disk and ejecta, whereas a resonant shattering flare doesn't require both, and you get a prompt precursor plus an afterglow, or potentially an orphan emission. Okay. So in this case, when there's no tidal disruption, the resonant shattering flare is really the only thing that can be happening. So it may be that this is the main signature, main electromagnetic signature that we want to find for a neutron star black hole merger. Here's just an example of the different afterglows. So this is the X-ray afterglow calculated. Here's the X-ray afterglow of the, this downslope here is the X-ray afterglow of the RSF. And then this is when the beam of the main gamma ray burst sort of comes into view. And you have the similar thing here for the, in the R band. In the radio, it's really hard to detect. So this is the peak for the radio. It's soon swamped out by, in this example, the gamma ray burst sort of coming in to view. But before SKA, I doubt this can actually be detected. You might have a chance for the X-rays. Optical is very difficult as well. You have to be very, very lucky. You know, you have to be sort of looking at it already, essentially. Okay. So I've told you a lot about the sequence of events, the dynamics that happens that causes these resonant shattering flares, and where we can expect to see these kinds of things. But what can resonant shattering tell us? What can we learn from these RSFs? Okay. Well, if you look at the time before coalescence versus the frequency, you'll see that a chirp basically follows these dashed lines, right? So here for a chirp mass of 1, it would follow this dashed line down. So at 100 seconds beforehand, it's at tens of hertz. And then as it gets down to a second beforehand, you're at 200 hertz, etc. Right? So these are just different chirp masses. Remember, a chirp mass is a combination of the two masses involved. So a neutron star merger is something like 1.5, chirp mass of 1.5. A neutron star black hole merger would be something like a chirp mass of 4.5. Okay, so let's say that we detected one of these things, and we see that this binary sort of follows one of these trajectories here, neutron star trajectory. As it's merging, we also detect a resonant shattering flare from it. Okay, if we can measure the time of that resonant shattering flare and compare it to the merger time, the chirp time, then we can actually just read off the mode frequency from the chirp signal. Okay, so coincident timing of a resonant shattering flare with the gravitational wave chirp detection means that we can just read the frequency off by looking at the timestamp of the resonant shattering flare. Okay, so that allows us to do precision asteroseismology of the neutron star, in particular the I mode of the neutron star. Okay, not only does this allow us to sort of immediately test this model, right? If we see a flare that occurs before the chirp merger, then we know that this is a precursor. This is most likely a resonant shattering flare, because it predicts a weak GRB-like emission seconds before the chirp coalescence, and that same measurement will give us precise timing, precise astroseismology of the neutron star. Okay, and this in turn can provide us with nuclear physics constraints. Okay, this was attempted with QPOs from magnetar flares in 2009 by Andrew Steiner and Anna Watts, and here they looked at quasi-periodic oscillations that occur after a giant flare, and basically they get sort of wiggles from the emission of the neutron star, and they interpreted those as oscillations that were due to toroidal modes. Basically, you're hitting the neutron star like a gong, and then you're looking at sort of the ringing oscillation afterwards. The problem with this is that they don't really know which frequencies should show up, which mode should show up the most in this case. So the advantage, so here they're looking at the frequencies of the different overtones, and they're comparing those to some example equations of state calculations. And sort of these are the same equations of state that I used for the resonant shattering flare. Now, the advantage that we had over the work done by Steiner and Watts is that we know exactly which mode must be involved, whereas they sort of have to guess based on the structure of the QPOs. There's also some question of whether these modes really decay slowly enough, or whether they're damped by a coupling to what's called the Alfvén continuum inside the neutron star. So how do we link these equations of state to nuclear physics? Well, one of the sets of parameters that we'd really like to know in nuclear physics is the symmetry energy, the nuclear symmetry energy. This is basically, if you look at the energy of a nucleon, of a nucleus, if the nucleus consists of an equal number of neutrons and protons, that would give you what's called E naught of some density. So density is the rho neutron plus rho proton. Okay, so that's the equal number. And then if you change the if you kept the total number of nucleons the same, but subtracted protons and added neutrons, that would increase the energy of the system. Okay, and that the rate at which that energy increases is called the symmetry energy. Okay, it's basically how much it costs to break the symmetry between neutrons and protons in a nucleus. And this is one of the important nuclear physics parameters that people have built giant several billion dollar experiments to measure. So here are the current experimental constraints on this nuclear symmetry energy J and its derivative L at nuclear saturation density. So here's the this blue here is the neutron skin depth experiments. This green swath here comes from what's called isospin diffusion. The yellow swath comes from lead dipole polarizability. The red here is from giant dipole resonance, and this orange is from nuclear masses. And all those constraints put together sort of give you this little quadrilateral in here. Okay. And the constraints from astrophysics, really from the neutron star masses and radii, sort of give you this hatched region here. Okay. So what we'd like to do, what we'd like to see is if measuring the measuring the I mode frequency can give us good constraints on in this parameter space of L versus J. Okay. So it turns out, so my student Duncan Neal and Will Newton, who's over in Texas, we sat down and we calculated the different interface mode frequencies for a huge swath of different equations of state, where we've varied the nuclear symmetry energy J, its first derivative L, and also its second derivative K, what we call K sim. And we found that the I mode frequency is mostly just dependent on the mean shear speed. So there's some spread that has to do with the spread of the global structure, the differences between the global structure of the neutron star that you predict from these different parameterizations. But you see that it mainly depends on the I mode frequency here on the bottom, mainly depends on basically the mean shear speed within the crust. In this particular case, it's the density weighted shear speed. So it's predominantly controlled by the shear speed at the base of the crust. Okay. Here, so the black X's here are sort of for our entire range of models, sort of some of which are semi-ridiculous combinations of J, L, and K. If we sort of limit ourselves to theories, to parameters that agree with pure neutron matter theory constraints, then we get this blue configuration. And if we sort of look at the situations that are similar to MSL0, a particular equation of state, if we make models like that, then we get shear speeds as a function of frequency that look like this. Okay, if we take though that MSL0 like model and we look at and we plot those shear speeds against J and L, against the symmetry energy and its derivative, we get these contours. So this is 3 by 10 to the 6 centimeters per second, and each of these is separated by 0.5 times 10 to the 6 centimeters per second. Okay, so putting those things together, we can actually work through and calculate the I mode frequencies as a function of the nuclear parameters. Okay, and that's what we do here. This is a 3D plot. I'll show you some slices in a second. So this is the different I mode frequency contours for the range of models that we looked at. Okay, so if we make some cuts, if we look at just the pure neutron matter theory constraints, we get for a measured I mode frequency of 120 hertz, you would get constraints on L and J that look like these. So these are really thin. Okay, if from say mass and radius measurements, we knew that the model had to look like an MSL0 kind of model, and this is just an example, then the frequency constraints would be very, very tight. Okay. If we sort of look at the error budgets involved and included the range of the fact that the resonance window means that you can only determine the frequency, the resonant frequency, to a certain precision, then that does, and sort of the worst case scenario, it does spread out the constraints that you can get. So for instance, here you have the spread both from the fact that K-sim is a free variable and that you have a resonance window. So you can see that these constraints, if you manage to measure the frequency, say 140 hertz, these guys are comparable to the current nuclear physics constraints from sort of these big expensive experiments. If you can limit yourself to particular models, particular classes of models, then it can do even better and give you sort of a 50% better constraint than current models. Okay, so in summary, resonant shattering flares are caused by resonant tidal excitation of an I mode, injecting energy into pair photon fireballs seconds before the merger. They're relatively isotropic. They're bright, and they should be easily detectable within the LIGO horizon, given a significant magnetic field. The energies we expect are about 10 to the 47 to 10 to the 49 ergs, with the duration of about 0.1 seconds. These can appear as short gamma ray burst precursors or orphan resonant shattering flares, which would look like underluminous, very short gamma ray bursts. There's a weak X-ray optical and radio afterglow, and if we can do coincident timing, then we can confirm the model and also determine that mode frequency, which lets us put constraints on the shear speed at the base of the crust and nuclear physics. This is all complementary to the sort of bulk properties that you would be able to get, which depend primarily on the core equation of state. So the complementary to the mass, the radius, the Love number, and the results that we're finding is if we get one of these measurements, we should be able to get comparable or even better than current experimental constraints on these nuclear physics parameters. One of the other benefits, or one of the main benefits observationally, is that resonant shattering flares do not require tidal disruptions, so they apply to a larger fraction of neutron stars and black holes. There's still a bunch of uncertainties with this model, though. We don't know the sort of rate of resonant shattering flares versus the number of mergers. It really depends on the surface B field, and thus on the agent of the accretion, and whether or not the field is frozen into the core or exists only in the surface. And Costas is the expert, of course, on how the field within the crust evolves and decays over time. So he's my go-to person to ask for these kinds of things. And we also would like to be looking at the excess, whether or not there's any excess in the nearby orphan, an excess of weak short gamma ray bursts that could be evidence of a nearby orphan population of resonant shattering flares. Okay, so that's all I had.
Thank you very much, Dave, for the wonderful talk. It's been very interesting, very exciting to have all this work, these results now. I don't know if anyone from the audience would like to ask any questions. Feel free to unmute your mic and ask your question.
Hi, I have a question. So, Dave, do you have any idea what would you get from a combined observation? Let's say if you managed to measure this this mode from a flare, and then you measure the properties of a merger that comes after that.
Yep. But that'd be fantastic.
I bet it would.
Yeah. So the main constraints on sort of neutron star physics that come from the post-merger stuff is whether or not the post-merger object is still a neutron star or a hypermassive neutron star. So the primary thing we get from those are the sort of upper limits on the mass. Either if it's a long-lived one, then the upper limits on the mass period. If it's a sort of supermassive or hypermassive one that's about to collapse after it loses rotational support, then we also learn something about sort of at least warm neutron stars. So things that aren't quite cold but are pretty warm. We mostly the dynamics after the merger are so messy. You can imagine how much sort of gastrophysics and magnetic field, the simulations are really, really tough. There's so many degrees of freedom that you lose because of there's so much dissipation involved that you can't really extract too much about the sort of fundamental physics involved. But it would be an amazing thing to see if all these occurred. before, I know in 1708-17, before the timings sort of were well known, I got a very frantic message from friends of mine that sort of worked on it, and they thought at first it was a precursor, but I looked at the data and said, you know, it can't be a resonant shattering flare because the durations are too long. So it would have been nice, but I'm still very hopeful that we will get one of these and be able to do this science and constrain nuclear physics.
Yeah, fantastic. Any other questions? If there are no other questions, I have to ask a couple of questions, Dave. What I was thinking of is, is your results affected if the core is superfluid? So you're doing some coupling there between the core and the crust. How superfluidity comes in the game, if it comes in any way?
Yeah, I mean, so I think the right way to think about this is if you want to calculate modes and you include a superfluid component, it's basically it'll basically cause a splitting, right? Where you have the response of the superfluid component, and then you have the response of the normal fluid component. And so there could be two separate frequencies involved. But we haven't done that calculation yet. Currently, we're just treating it as a normal fluid. I suggested to Duncan that we start looking at this, but I think that's what would happen. You'd basically have an I mode that exists because of the transition between the pure fluid, the normal fluid and the crust. And then you also have something, maybe it's at a similar frequency or maybe slightly different frequency for the transition between the superfluid and the crust. Just because of the different bulk properties, right? So you get a slightly different response and a slightly different frequency.
Yeah. I don't know.
So you may get, it may be possible to get more than one. I'd have to think about where that transition occurs.
Right. Okay, that's all very exciting. Any other questions? So I'll go also with my second one. You said something that there is this scaling with the magnetic field square. So in the case where we have probably seen the precursor, which is related to the shattering flare, what's your guess for the surface magnetic field?
It's hard to say because these ones have not been, the redshifts are tenuous for most of them. I think they have to be, you know, above 10 to the 13.
All right.
Okay. So like, I mean, if the B fields were 10 to the 12, then 10 to the 13 surface fields isn't, sorry, if the dipole field is 10 to the 12, then 10 to the 13 surface field isn't crazy.
All right.
What worries me more is these neutron stars, when they most of the binaries that manage to merge after a very long time, right? Unless you get very lucky and they happen to kick themselves into something close to a merger. Right. So the real question is, how long can a strong surface B field last?
That's true. On the other hand, in the double pulsar, one of them is a millisecond pulsar, the other has a the magnetic field is stronger, is 10 to the 12, the dipole component, because the one that became
but what would be really bright would be something with, like, you know, magnetar strength surface field. But if it's pure crust, that can't last more than, I think you told me, 100 million years at most.
Yes, this is with the number we're getting, but still it's not.
But if it's core, then it's a different ballgame, right?
Sure, exactly. All right, so I'm done with my questions. I don't know if anyone from the audience has any questions. Andrea?
I'm not sure I have a question. I just wanted to ask about those kilonova.
Kilonova, yes.
Yeah, so do you detect this as a as a single signal, or is it like a signal that repeats itself? Or
Oh no, it's a very slow signal that peaks and then falls off on the order of tens to hundreds of days.
Because I was wondering, those excitations don't happen at the same time, right?
No.
Okay.
The kilonovas happen well after the merger, days after.
No,
Basically, it takes time for the shell to expand out enough so that light can escape.
Okay. I wanted to say that I was thinking, because the merge. Can you give me 1 second? I'm sorry, I'm a bit anxious.
No, it's okay. Don't worry.
So I'm thinking the process goes like the nuclei, they merge together to form bigger elements.
Yes, that's right.
Then they release the gamma rays.
So the gamma rays come from the gamma ray burst.
Yeah, not gamma rays. They emit some radiation.
Yes, that's right. Yeah.
And I was thinking, like, how long does this process last? Because I don't think it would be simultaneous. And
you're right. You're right. So the dominant heating comes from I think nickel 56. And so it's, what's the half-life of nickel 56? I don't know off the top of my head, but it's whatever that is. That's the dominant time scale. And it's really it's a very hard thing to actually get too many spectral signatures from, because there's so many heavy elements, and we're pushing up into the lanthanides, and the lanthanides are just a forest of lines. So everything just gets sort of caught up in this expanding bubble. So you don't get, like, even though the heating may occur faster, until basically the system becomes optically thin, you don't get too much emission from it.
Okay.
Right.
Thank you very much.
All right. Brilliant. So I would like to thank Dave again. Sorry, George, you want to ask the question?
Yes, I have one last question.
Sure.
Cheers for the great talk.
Oh, thank you.
Can I ask, how about the interplay of the magnetic fields seconds before the merger?
Very good question.
Because can these flares be produced via magnetic reconnection from the collision of the two magnetospheres?
No, that's not strong enough, but it's a very good question. You can still get a signal. Actually, one of the very interesting signals you can get is some work by someone that Kostas knows very well, his old supervisor, Maxim. And this is very cool. It's if you have a conductor moving through a magnetic field, you might know that as a unipolar inductor.
Okay.
And so the surface of the neutron star, let's say there's a weak neutron star and a stronger neutron star in terms of magnetic field. As the weaker one moves through the magnetic field of the other one, it can cause a current to occur that sort of links the neutron stars via the magnetic field. And that can cause X-ray emissions. Unfortunately, the amplitude of these emissions is really quite low compared to the precursor emissions. You'd also expect them more in the X-ray than the gamma rays.
Yeah. Okay.
But it's a really cool mechanism. You actually see this mechanism in a very famous paper by Peter Goldreich in the interaction between Io and Jupiter. And in that case, with those sort of parameters of magnetic field and conductivities, you get radiation that's like 10 centimeters in wavelength.
Yeah,
and it's very observable
radiation.
So yeah, so it's very, very cool. That sort of the toy classroom physics model of a unipolar inductor can be seen in Jupiter and its moon.
It's very exciting.
Yeah.
Thanks again for the talk.
No problem.
Yeah. Dave, thank you very much for this talk. Thank you very much for your time. We are very grateful. So for everyone in the audience, we will be having our second seminar next week, same time, same link. It will be Rainer Hollerbach, who's going to talk about the magneto-rotational instability, the so-called MRI. And I'm sure this will be exciting as well. But for now, let's thank Dave again. And we're looking forward to have you here and take you out to dinner as we normally do after seminars. Thank you very much.
Okay, I'll see you later.
See you. Bye.
Bye.